Afternoon, everyone. My name is Herearii, PhD student, first year at Université d'Angers. And today I would like to present to you an unsupervised method to extract the vegetation in foreground of a row based on a monocular color imaging. So the context behind is in fence structure of arboricultural plants. Agronomists extract usually the vegetation in foreground using a manual extraction by hand in a point cloud generated by a LiDAR sensor or a stereo vision technique. The need behind is the point cloud generated by a LiDAR sensor, which is expensive, or a stereo vision technique, which can be sometimes difficult to set up for data collected outside in orchard. Our solution is to extract the vegetation using a color image generated by a color camera. So we would like, based on a color image, estimate the monocular depth. So we can use some object in a color image to extract the depth information in image. So we can use the occlusion between two objects, the relative size, the cast shadows, the shading, the distance to horizon, the texture gradient, or the linear perspective. So we leverage depth model to generate the depth map from a color image. So you can see some example. So here in front of you, an estimated depth map where the color intensity means the proximity with the sensor. And at your right, you can see the depth map in a 3D space, so the same depth map in 2D and here in 3D. So our method, we have at the beginning a color image of a vineyard here. We estimate its depth map using an AI model named Depth Anything V2, where we predict each pixels to an estimated distance measured between 0 and 255, where the pixel is information between the object and the camera. So this algorithm is structured in three parts. So we have the color image. We extract the global features in color image using the Dino V2 encoder. In the second step, we reshape the features into 4-scale, compress the channel, and extract the global context and Champy boundaries to get at the end information where we upsampling the map to the initial scale, so we get at the end the depth map. Once we have the depth map, we study the histogram of the distribution of the pixel of this depth map. So as you can see in the depth map in histogram, you can see the foreground of the row closer to the camera, and here the row behind in the background. So we detect the two row here, studied the maximum in the histogram, and between the two elements we can detect the threshold to separate the foreground and the background. So it is the minimum value between the two elements here. So we have the depth map, and we applied this threshold to separate the background and the foreground. So here we have the foreground segmentation where we include all objects, the leaves, the fruit, the pole, and the wire. Now we will detect the vegetation based on the input image. So we come back to the beginning, so the color image. And here we detect all the vegetation on the image using the grounding Dino 1.5 combined to the SAM2 to detect the vegetation in image and to segmentate this element. So we define vegetation with two elements, so the green region in the image and the foliage, and we use our AI algorithm to extract the vegetation. So here at the beginning we have the color image and the prompt text, so the green region and the foliage. We use the grounding dino 1.5 to detect the region where the vegetation is located in our image. So first, we extract the features from image and we convert the text in the token in the first part of the grounding dino. So we fuse the vision language themes and we get the text features and image features to put into the decoder where a bounding box is generated to localize the region of the vegetation in the image. When the box is generated, we use the SAM2 to segmentate the vegetation in image inside the box. So in the SAM2, we use first the color image to extract some features to embedded image. The second part is to convert the boxes in token to be adapted to the embedded image. And at last, we extract some global context and sharpen boundaries in the task mask encoder to generate a mask of segmentation of the vegetation. So here we have two elements, the foreground segmentations and the vegetation segmentation. We would like to detect only the vegetation in the foreground, so we make an intersection between the two elements, and we get this output of our method, so the vegetation in foreground in the image. So to sum up, we have our method divided in two parts. So first we segmented the foreground, and the last is the vegetation segmentation using AI models, so grounding dino and SAM2. And the output is a binary mask with vegetation in white pixel. So this method we tested in some fruits, so the banyan and apple. So the apple image, we have some image taken in Europe and Asia. So the result is good. So we had some good performance for the banyan and apple in general. The robustness is good because the fruit on the image is inside of the output of our method. We remove the poles in the output, but we have the wires on our image output. The robustness is the sensor cost, which is reduced. So any type of color camera can be used. I mean the action camera or smartphone. The time inference is reduced. So we have 1 minute by image in average for 15 images studied. To conclude, we have a generic method for any cropped, any camera or field settings without model retraining or site-specific tuning. We operated with zero labeled data or external depth sensor, so the cell itself provided all cues. We returned a clean plant-only mask that ignores post, wire, and distant background, and needs nothing more than a single color photos, enabling a low-cost, lightweight workflow. So this method is deployed on MapAI, computer vision and image processing software, so it's available for everyone. The perspective behind is to study the foreground, the vegetation in foreground, so you can study the disease, so the mildew here in a vineyard, or to count apple on an apple tree. So thank you everyone for your attention. So I'm available to reply to your question.